All right, page 157 in your textbooks. You answered 3 questions for homework over the weekend and did just 1 problem. Question 16 through 18 and problem 5. Problem 5. Yeah. Problem 5. Yeah. Problem 3 was like a week ago. It's okay. We'll have you help us with problem 5.
I wrote 3 and I did 5.
No, you didn't do 5.
Didn't?
No. Yeah, you did 3. You wrote 3 and you did 3. But you'll do problem 5 for us now. Oh, well, in just a moment at least. All right. Question number 16. What formula specifies the period of a pendulum? Michael.
The formula that specifies the period of time in a pendulum is T equals 2 pi times the square root of L over G.
Good. Number 17. What are the 4 laws of a pendulum? What are the 4 laws of a pendulum, Kendall?
The 4 laws of a pendulum are: the period of a pendulum depends on the square root of its length. The period of a pendulum is inversely dependent on the square root of the acceleration due to gravity. The period of a pendulum does not depend on its mass, and the period of a pendulum does not depend on its amplitude.
I know the last 2 were correct. I was distracted, number 1, looking for a tissue, and she has no tissues in the science lab. Who does that? Number 2, Audrey found her homework. I didn't look carefully enough at the questions. She was showing me the previous night's homework. So she does have the correct homework, so that's happy. What were the first 2 laws of the pendulum you said? It's a Monday.
It was a long one.
It was a long one. Just the first 2 parts.
The period of a pendulum depends on the square root of its length, and the period of a pendulum is inversely dependent on the square root of the acceleration due to gravity.
Yes, good. All right, number 18. How does a physical pendulum differ from a simple pendulum? Audrey.
A physical pendulum differs from a simple pendulum in that a single pendulum doesn't exist in a real world, for it can't be suspended on a massless connector.
Good. A physical pendulum exists. A simple pendulum doesn't. All right. That's the big difference. Good. All right. We'll get to pendulums. It's pendulums. Pendulisa. All right. We'll get to pendulums in a little bit. For now, let's go and review some stuff we talked about last week before the 3-day weekend. And we had looked at what's called uniform circular motion. Michael? What is uniform circular motion?
It's motion that follows a uniform path along a circle.
Kendall, what is uniform circular motion, since you laughed at him?
No. It's circle. And it's something to do with velocity. Same velocity. Something.
Audrey.
Constant speed. On one path in a circle.
Motion at a constant speed in a circular path. What is it, class? Motion at a constant speed in a circular path. Not a constant velocity. Because if it's going in a circle, the direction's always changing, right? So there's an acceleration. What kind of acceleration does an object in uniform circular motion experience, Kendall? Or might I ask, in which direction does acceleration act? Inward toward the center, so we call it
Centripetal.
Centripetal acceleration. What's the formula for centripetal acceleration? Anyone? A sub C
equals v squared over r.
There we go. And in order for an object to accelerate, Newton says there has to be an outside force present. So to find centripetal force, that's the force that causes centripetal acceleration. What's the equation, class?
mv squared over r.
mv squared over r, since F equals ma, since this is a, v squared over r, ma is the force. What were some of the different centripetal forces we talked about? Audrey?
Gravity.
Gravity for planetary motion.
Tension.
Tension for something swinging around and around on a string, or whatever. You know, you've seen the, Miss Morse has this little springy thing on her keys. Have you ever seen her twirling the keys on her finger? Yeah, the springy thing has tension in it. And so centripetal force. Next time you see that, think, centripetal force. Anyway, other ones.
Friction.
Friction, certainly.
And the weight in the X.
Yeah, if they have a banked surface. I actually watched some auto racing this weekend. I was not feeling great, family wasn't feeling great. So Sunday afternoon, while we all weren't feeling great, we sat around on the couch and we watched IndyCar racing, Formula One racing, and it was cool to see cars going 200 miles an hour, open cockpit, death just awaiting you. It's great. Anyway, by the way, for every action force, there's an equal and opposite reaction force. What is the center fleeing force called? The outward force. Centrifugal force. There we go, centrifugal force. From there we talked about motion that repeats itself over and over again after the same lapse of time. What is this called, class? Motion that repeats itself after the same lapse of time. Periodic motion. Now, specifically, if the periodic motion consistently follows the same path, we call it oscillatory motion. And if this oscillation continues to take place over the same path, over the same amount of time, and it's caused by a restorative force that's proportional to displacement, now we call it simple harmonic motion. There we go, third tries the charm. All right, so we looked, for instance, at the motion on a spring, right? And we had an oscillatory motion. Of course, this isn't the only example of periodic motion, right? But it's an example of periodic motion as long as it follows that consistent path, though it's got a little bit of a swing to it at the moment. But if it follows that same path, class, then that is oscillatory motion. Just by virtue of repeating the motion over the same amount of time, that's periodic. But there is a restorative force, right? The upward force that pulls the weight back up, class, that's the restorative force. What is it that pulls it down? Weight, specifically, the pull of gravity on an object's mass. And if I were to just let it hang still, or roughly still, we would say that the object is at equilibrium because the restorative force upward and the weight downward are in balance. To cause the oscillation to begin, you have to create an imbalance of forces, right? Add a force, either add a force upward, which makes the weight greater than the restorative force, and it goes into oscillation, or pull downward, adding to the weight, which makes the restorative force increase. Either way, we create this oscillation. And the time it takes to oscillate just once, class, we call period. How do we represent period? What letter represents period? T. Because remember, period is the time it takes. We measure period, class, in seconds, the time it takes to oscillate once. This time it's not swinging, it's just going straight up and down. That's much better. All right. Now, the faster it moves, the less time it takes to oscillate, the more rapidly it oscillates, the more oscillations it accomplishes per unit time. Number of oscillations per unit time, class, we call frequency. We represent frequency with the letter F. And we measure frequency in hertz per second, or hertz. And what's the relationship between period and frequency, class? They're reciprocals. They're reciprocals of each other. Frequency is the reciprocal of period. Therefore, period is the reciprocal of frequency. There's reciprocals of each other. Seconds and per second, reciprocals. By the way, I could get this to oscillate as it is, or, by the way, it did ding the counter. Miss Morse was not happy about that. She's like, so, did you scratch that counter? I'm like, I don't think, oh yeah, I did actually. I shot the mass up and it fell off. I actually bought this for the school though, so I'm like, but I paid for this table, so, you know, if I want to ding it. She's like, okay. So I'm like, note yourself, buy things yourself so you can mess them up if you want. So if I pull it down more, okay. Now, this oscillation is slightly messed up because it did go all the way to contraction. But this is a greater distance that it's oscillating. I could also get it to oscillate just a little tiny bit, which is much safer for the tabletop and Miss Morse's blood pressure. And so the distance from equilibrium that it oscillates, that's called, class, amplitude. What effect does the amplitude have on the period, class? None, right? It moves more slowly, which makes it take the same amount of time. It moves more quickly, so it takes the same amount of time because it's going a greater distance. greater distance still, but it's also moving more quickly. Why? Because you get a greater imbalance of force. Greater imbalance of force gives you greater acceleration, F equals ma, right? Greater acceleration, greater velocity. Greater velocity and greater distance cancel out to get the same amount of time. So amplitude doesn't actually affect the period. How do I calculate the period for an oscillating spring? And this brings us to the problem that we worked, problem number 5. What's that equation, Kendall?
2 pi.
Which, by the way, the 2 pi refers to the cyclical nature, right? It's not going in a circle, but if we wanted to, we could track the progression cyclically. So that's where the 2 pi comes in.
The square root of m over k.
Good. T equals 2 pi times the square root of m over k. So m, of course, class, is the mass. What would happen if I increased the mass? What effect would that have on the period? It would increase, which means it would take more time. So we showed this in class, remember, last time, but I'll show it again. If I put more mass on here, let's just swap it instead of adding it to. If I put more mass, you can see that it takes a longer amount of time to complete the oscillation. If I put a smaller amount of mass on here, we can see that it oscillates more quickly. So mass, certainly. What about the K? K stands for, class?
Constant.
Spring constant. How do I find the spring constant? Anyone? In their defense, by the way, if you're watching on YouTube, you're like, how do they not remember this? They had a 3-day weekend, so you might be watching this the day after watching the previous lesson. They've had 3 days off. I'm trying to help y'all out here. All right. mg over x. Or you could say the force that causes the oscillation over the stretch. Usually that would be a force of weight. Now, that means that K could either be measured in newtons per meter. Remember, x is the amount of stretch, which is meters. Or if you have the mg over x, since the g has meters per second squared, the meters would cancel these meters, and you'd end up with
Kilograms per second squared.
There we go. So either one of these units. The kilograms per second squared is more intuitive because it cancels with the kilograms. You take the square root of the second squared to get seconds for your period there. So these were the equations that we needed to do problem number 5. Now, Audrey, I did promise it to you, and I don't want to go back on a promise because I'm not that kind of teacher. So number 5, go and read it for us, Audrey. Next time I'm going to find the right homework first time. Yeah, you will.
An object on a spring whose constant is 30 newtons per meter oscillates at a frequency of 10 hertz. What is the mass of the object?
All right, so they give us 2 numbers here, Audrey. They give us the
spring constant.
as 30 newtons per meter, which is 30 kilograms per second squared. And they also give us
frequency is 10 hertz.
And they ask us to find the
mass
of the object. Now, I do not have an equation that relates these 3 variables. I do, however, have an equation that relates mass and spring constant. But mass and spring constant, class, would be related by
the constant formula.
M and K appear in the same equation with what other variable?
Oh, the time.
Either period, or you could say this one, right? They both have M and K in them. G, of course, being a constant value for our purposes. Stretch could come into play, but I don't know the stretch. Or the period could come into play, but I don't know the period. Or do I? If the frequency is 10 hertz, that means 10 of these in a single second, then I do know the period. What is the period? How long does it take to make a single up and down? A tenth of a second, right? If it makes 10, I mean, can you imagine the kind of vibration you get? Almost picture a string when you pluck it vibrating, right? So, as opposed to a spring, which, I mean, that's a really fast vibration. But 10 cycles, 10 full oscillations in a single second means you've got 0.1 seconds, or a tenth of a second, for each individual oscillation. So I do know the period, I do know spring constant, and I wanted to find mass, and that was going to be the key to the problem. I need to rearrange the equation then to get the mass by itself. Audrey, what do we need to do?
You'll do T over 2 pi squared times K.
All right, so we'll take the period, which is 1/10 of a second, 0.1, or 1/10 is a fraction. Divide that by 2 and divide it by pi, or divide by the quantity 2 times pi. Square that, multiply all of that by the spring constant, which was 30 newtons per meter, and which is a pretty strong spring, about like my strongest, and this is a very small amount of mass. I don't even have a mass this small. What do we get for the mass, Kendall? Okay, better be calculating it then. I didn't see a calculator, so I assumed you had it. Michael?
I have 11.843.
Audrey?
7.59 and -3.
Yeah, 0.00759 blah 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 kilograms. I'm actually going to change it to grams and move the decimal back 3 places. 7.6 grams was the mass. Or you could say 7.6 e -3 kilograms. So work it out again on your calculator. Make sure you get the same answer Audrey had. 0.00759 is the mass. And again, my smallest mass I have is 10. I believe this thick spring is about 30. So but like I say, as soon as I pull it down anything, that mass is going to go flying. So somehow, some way, I assume it's probably not a completely compressed spring. It's probably slightly sprung out to start with. But I mean, I don't even know how to get it to how do you even get it to oscillate at all? I mean, I don't even know. It's sort of kind of wiggling, and that's about it. So, yeah, this is perhaps more theoretical than practical. Again, unless you start with a slightly sprung out spring to begin with, I'm not sure. Do we get the 0.00759? All right. Questions on problem number 5. Questions on 5. All right. I believe I gave you the term simple harmonic motion. Check your notes. I think I asked it as a review question, so I assume that means I gave it to you as a term. You're reading page 152. Before we get to the pendulum, there's a really interesting picture, a really interesting graphic, a little cartoon, and there's a world-famous hole in Australia, and there's a lady tourist who's all set to take her husband's picture, and there's a sign that says, "Do not lean against fence," and apparently some dry rot has set in, and the guy crashes through the fence, and she's all shocked, and the guy's like, "Don't worry, he'll be back." And did you think about that? Why? Like, if it's a world-famous hole to Australia, again, this is imaginative a little bit here, but imagining a hole that goes from where we are, for instance, all the way through the earth to Australia. Wouldn't he just fall till he got to Australia? Like, how's he going to be back? Is he going to climb back up the hole? Did you think about that at all? Or did you just kind of look at the goofy picture like, oh, whatever? Thoughts? Comments? Oh, okay, so I like the finger motion because you kind of give the idea, right? So if we imagine the Earth, right, as a sphere, we're going to do a circular cross-section, right? And here's the world-famous hole to Australia, and here's Australia, the land down under. So there's this hole, theoretically. Now, again, I know in reality it's impractical because as you get toward the center of the Earth, it gets very, very hot, right? You've got the magma, you've got the molten outer core, and then the inner core. It's all extremely hot in there. At least that's what they believe to be the case. No one's actually been there. But based on tests, that's what's got to be the case. But in theory, if it weren't like scalding hot right there, as a person begins the descent, remember where gravity is generated, from the center, correct? So the pull of gravity is all based here at the center of the Earth, which means as the object gets toward the center, acceleration due to gravity, the object is going to begin moving faster and faster and faster and faster and faster and faster and faster until they get to the center of the Earth. Will they come to a screeching halt right there? No. No more than as the object is displaced from equilibrium, it rushes up to equilibrium and stops, right? No, its inertia causes it to go past, correct? But eventually, the weight pulls it back down again. So what happened is the object would accelerate faster and faster and faster and faster and faster toward the center of the Earth, and then its own inertia would cause it to race right past the center. But as soon as it gets past the center, which direction does gravity act? The other way, slowing it down. So it races fast and begins slowing down, 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 until right as you would reach the other side, theoretically, if you could grab onto the side, you're free, and you don't have to get your picture taken. or have to pay for the broken fence. Except your widow would have to pay for the broken fence, or at least perceived widow. But if you don't grab onto the side, right as you get to the other end of the hole, you slow down. Gravity has now decelerated you back to 0. And then you begin accelerating this way. Back, faster, until you get to the center of the earth. But then again, your inertia, you blow right by it. And if your wife is ready with a lasso, she can grab you right as you get out, right? She just won't lean onto the fence to hold on because it was weak and broke under you. So it's going to break under her and you together. So anyway, so you race first back here until right as you get to the center. If she doesn't lasso you, she says, hi, bye, as you begin descending back and forth. Now again, if there's air resistance, which of course there would be air in the hole, okay, if indeed there was a hole, there would be air. So there would be air resistance to slow you down. So each time your oscillation would get further and further from the center until eventually the oscillation would kind of come to a standstill, kind of like this. If I left it long enough, this would stop oscillating. Why? Well, there's friction in the spring. There's minimal air resistance. Eventually it would come to a stop. And eventually the same would be true here at the center of the earth. You just kind of just stay there, so to speak. But if there were no air resistance, if somehow this were in a vacuum setting, right, then the object would just continue oscillating back and forth, back and forth, back and forth. How long would it take? A really long time. Would your heartbeat rate be able to survive it? Probably not. Okay, so probably you're dead before you ever got near the center of the earth, and that was ignoring the heat factor, right? So we're ignoring that altogether. Probably, but again, it's just cartoon, right? Now, here's the thought, though. Here's the thought. Any of you ever heard that hell might be at the center of the earth? Anyone ever heard that theory? I don't know that that's true. The Bible doesn't tell us where hell is. There have been certain claims about people hearing screams when they dug down deep in mines in Russia and stuff like that. I don't know how much of that's true. I don't know how much to buy into it. I know people sometimes hear things because they have fear in their own heart. You're deep in this hole, start to fear maybe a cave-in, or you just get claustrophobic, so you hear things. I don't know anything about all of that. But I do know this. The Bible tells us that at the end times, death and hell are cast into the lake of fire. The lake of fire is a separate place from hell then, right? I know this isn't a theology class, but bear with me. All right, death and hell are cast in the lake of fire. How could death be a thing? Well, death isn't necessarily a thing. Death is a place where things die. Where's the only place in the universe that things die? Earth, because it's the only place where things live. There is no life elsewhere, despite our greatest efforts to find it. Right? There is no life elsewhere, so there is no death elsewhere. Also, remember the Bible says that God makes a new heaven and a new earth. The old earth has been done away. Well, that would be the way I interpret that very possibly to mean, and I'm not saying this dogmatically, but it stands to reason that God takes planet Earth, which is where all things die, so that's death, and if hell were to be in the center of the earth, right, cast that planet into the lake of fire. Some people say maybe that's the sun. I don't know. Whatever, okay? God is big enough to have whatever he wants, but maybe it's the sun. I don't know. Cast the earth into the lake of fire. Now, here's the thought. The Bible compares hell to a bottomless pit, right? A bottomless pit, meaning a pit or a hole in which you fall forever. Now, you know this. I'm like, how could you fall forever? Well, if you were in outer space and you were to fall off of the International Space Station, you would have a sensation of kind of floating, though. That really wouldn't feel like falling, would it? Falling has to have a pull on you. Like, for instance, the pull of gravity. Also compares it to a lake of fire, where there's burning, right? It also says that hell is dark, so it's a burning blackness. Now, if the center of the earth is, as they say, molten metal, scalding hot, and God saw fit to put the souls of man into the center of the earth, oscillating, falling forever, bottomless pit, and burning blackness, that would make some logical sense. Again, that doesn't mean hell's at the center of the earth. That is not my claim. But it just gives one thought that perhaps that is the case. I personally don't want to find out. Okay, so I am thankful that it's not up to me. I'm thankful that God took care of it, and that simply by putting my trust in what Jesus Christ did on the cross, he paid my sin debt. I don't have to pay my sin debt for myself. So I am thankful for that, certainly. But anyway, just a thought that kind of spurred by this world-famous Whole of Australia graphic. All right, any questions, comments on that topic before we move on? All right, let's talk about the simple pendulum. So in your notes, simple pendulum. First of all, it doesn't exist. But we are going to ignore that fact because we work in the realm of the ideal. We ignore things like air resistance when they cause us problems. So we're going to ignore the little fact that a simple pendulum does not exist. Here's your definition, and you'll see why it does not exist. A simple pendulum is a freely swinging mass suspended from a thin, massless connector. A freely swinging mass suspended from a thin, massless connector. A freely swinging mass suspended from a thin, massless connector. Can you have a connector that is massless? No. So can you really have a simple pendulum? No. But I don't think it's worth throwing out the idea in this sense. Compared to a mass, might a connector be comparatively massless? For instance, if Kendall were hanging from a rope and she were swinging. Now, Kendall doesn't have a great mass to begin with. Kendall is, and if we were going kilograms here, I'm thinking about 45 kilograms or so. Somewhere in that 100-pound range. Am I about right? Give or take. So she's only about 45, maybe 50 kilograms. I can't see her topping 50 kilograms. That'd be 110 pounds. I don't see any way on God's green earth you're 110 pounds. Okay, so she is not particularly, but let's suppose the rope that she's hanging from only weighs a pound. A half a kilogram, roughly. Compared to Kendall, it's virtually massless. For instance, maybe you catch a 10-pound bass, and you catch it on, let's just say, 10 or 20-pound test line. Well, as it oscillates, swinging back and forth on your fishing line, the line might as well be basically massless? The fishing line has mass, but compared to the mass of the object, it's virtually massless. Now, if I took a tiny little 10-gram mass, and I hung it right here, this string might actually have about the same mass as that 10, okay, not quite, but I mean, it's close. So in this case, the mass of the connector is perhaps similar. But if I even went to, say, 200 grams, this is nowhere close. So although it's not massless, it's close enough that we can still take some of the principles and apply them. So this is not a simple pendulum. It's what we call a physical pendulum, meaning it actually exists. There really is mass to the connector that will mess with the math. But it's not going to mess with the math much. What messes most of all is the fact that it's swinging at a weird angle kind of thing because of the way the knot's tied and the way it's suspended. Anyway, that is unfortunate. I wonder if I swung it this way, if it would try to come around to normal. I don't know. Anyway, but we get the idea of a freely swinging mass. Now, if I have it just sitting here, it's not swinging at all, right? Then at this point, I'm going to see if I can slide this down just a little more. I tied it a little tighter to the bar than I wanted to. Let me get this out of the way. I'm going to move this up out of the way like that. Okay. Give myself a little room. I'm going to go side to side with it this time. All right, when it's hanging here perfectly vertical, we know that there's weight downward and there's tension straight upward, correct? These two forces are perfectly in balance. If you would note this for a simple pendulum, the vertical position is called equilibrium. The vertical position is called equilibrium. The vertical position is equilibrium. Amplitude is not achieved by pulling down, because pulling down does nothing, right? It's not like a spring. What would cause it to oscillate is if I pull not downward class, but backward or sideways, right? As I pull sideways, now what I've done is I've added a horizontal force. It still has weight downward, remember the kid on the swing. It still has tension upward in the y, but it also has tension forward now in the x. I've got an applied force holding it backward. And as soon as I let go, there's an imbalance of forces. So what's going to happen? It's going to accelerate forward because of the tension in the x. Now it's going to accelerate till it gets to this equilibrium position and it stops just like that, right? No. No, because of inertia, right? As it accelerates forward until it gets here. Now, as it's moving past equilibrium, tension now begins to pull backward until, at whatever distance I pull backward, it comes forward. And then that tension, kind of like we talked about the Earth slowing down, that tension has stopped it, so it goes backward, and it just goes back and forth. Now, cool people have great big pendulums, and they pull it back right up to their nose, not quite touching. And they let it go across the room. And it swings back, and right before it gets to the nose, it stops. And it goes back and forth, just keeps coming back. Now, little by little, it'll start swinging less and less. Why? Because there is actually friction, because where there is mass touching something, there will be friction. Right? If you just sit on a swing, even if you got a good push, eventually the little kid will stop swinging. Right? Because there's friction, there's some air resistance. It's friction more than anything that causes the stoppage. But you've even noticed it's not swinging as far back. I pulled it back almost to the metal pole. And on the first swing, it goes almost back to the metal pole, but little by little, it begins to lose just a little. A true simple pendulum would not lose that displacement. That displacement would continue in perpetuity. So what we're going to look at for amplitude is the angle at which it is pulled back. So if you would, make note that the amplitude is the angle of displacement. For those in pre-calculus, theta might be a good way to represent it. That's how we're going to indicate it. Theta would be the amplitude. Now let's consider something here with our pendulum. I'm going to go ahead and pull it back here, and I want you to calculate, or just kind of clap your hands if you would, when it hits this position again. And each time it comes to its full back position, we'll kind of clap so we can hear, if you will, the period. All right, do you have a rough feel for the period? Pretty good idea, okay. Now I'm going to put a larger mass on here, and let's see what happens with the period. All right, thoughts? Seems to be the same, doesn't it? Let's put a smaller mass on and see what happens. Thoughts? Still feels like the same thing, doesn't it? All right, so we can conclude evidently the mass doesn't seem to affect the period of the pendulum. Let's go back to the medium weight here that we had, which was the 200 grams. But mass doesn't seem to impact it. Let's try this now. I'm going to pull it back again, and we should still hear that same rhythm we've been hearing. All right, now, instead of pulling it back all the way to here, let me pull it only halfway back. Thoughts? Still felt like the same? Okay, let me try this. Let me only pull it back this little bit here. Thoughts? Still feels the same. Now, wouldn't it, I mean, if I pull it back further, shouldn't it take longer? Why not? Greater tension in the X. So when I let go, greater acceleration, greater speed, it's going to move more quickly. So we get the same amount of time traveled, even though it's a greater distance, it's moving at a greater speed. When I move it like this, I mean, it's barely moving at all. It's so slow, but it barely had to go anywhere. So it still takes the same amount of time. All right, now let me put this one up out of the way, and let me slide this one over here. as long as they don't get tangled. I don't think they will. And, oh boy. Yeah, it's going to be a little too short. Let me do this. Let me do the old-fashioned when the swing is too short for you. Or the swing is too low for you, kind of thing. Okay. All right. So now let's clap out the rhythm. Thoughts? Felt the same as the last one? I felt like it took longer. Let's do this. Let me switch these out. Let's go back and let's kind of compare them straight up to each other. All right. So let's start here. Okay, and now let's go back to this one. I feel like it takes, I feel like I'm ready to clap and it's not quite there yet. So I feel like it takes, but it's not much longer, right? It's just a little bit longer. Okay? Let's compare. Stay. Get him out of the way. All right, let's compare this one. Now we've already determined it doesn't matter how far I pull it back, right? So, and the mass doesn't really matter. Okay, so let's start it here. What are your thoughts on this one? Feel like it's faster, okay? So if I were to go, because I went longer, it took longer, shorter took less time, so what should I be anticipating with this short little guy? I should expect this to be even faster, right? Let's see. So what do we notice then? If the mass doesn't really affect anything, the distance I pull back, or the amplitude, the angle really technically that I pull back doesn't really seem to affect anything, but the length certainly does. Now, what is it that drives all of this? It's ultimately the weight, right? If there were no weight, if I pulled this back, it would just hover, right? So there has to be a pull. Oh, notice self, don't pull back quite so far. There has to be a pull of gravity to pull it down and forward, right? Because it is that weight that produces the tension, right? And the tension is what drives it all. Now, if gravity were to get stronger, it would accelerate more rapidly, correct? So a stronger gravity, for instance, if we were to go down toward the center of the Earth, down in one of those mines, gravity would be stronger. If we were to go higher up, maybe on top of Mount Everest or something, just to swing a pendulum, which seems like an infernal waste, maybe it's just for the experience. You know, I got a friend in Nepal. He does treks and stuff in the Himalayas, so I don't think he's scaled Mount Everest yet. But I'm waiting for that one. Anyway, but if gravity were weaker, it would not have that initial movement as quickly, right? It would not accelerate as quickly from its displaced position. So really there's two things that affect the period. So we have 4 laws of the pendulum. If you would get these in your notes. I know you wrote them for homework. Let's write them again for this. 4 laws of the pendulum. Law number 1, period depends on the length of the connector. Period depends on the length of the connector. Now, it doesn't depend strictly on the length. For instance, if I were to double the length, let's test something here. Okay, let me get all these strings hanging down here. This first connector, I would have to measure, I don't have the meter sticking here. All right, but this first connector and the third connector, it's not perfect, but do you see that this third, well, I guess for you it would be the second connector and fourth connector from your perspective. Do you see that this appears to be about twice as long? Is that fair? About twice as long? Okay. Let me go and hang a couple masses here. And if it depended proportionally to length, then this would literally make 2 oscillations in the same amount of time. but it doesn't make two oscillations in the same amount of time. It is definitely oscillating more quickly. In fact, if I were to, let me turn the cat, now I'm really throwing the weights up. They're swinging all over the place. Let me turn it this way and kind of and show it again. It's not quite 2 for 1, is it? Otherwise, you'd see a bump, 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 bump for every one back and forth. They do a full back and forth for every one back or forth, right? And it's not quite doing that. So clearly, it's not one of these cases where it's a perfect proportional. If we were to do some tests, and people did, and we'll actually do a lab here in the next lesson or two with this, with a timer called a photo gate timer. It's one of those where, I don't know, you ever, garage door openers. At the bottom, there's a little light beam, invisible light beam, infrared beam, that it shoots out, and there's a receptor on the other side, and if you break the beam, the garage door goes back up so it doesn't crush you like a bug, because the bug doesn't trip the beam. Anyway, well, it's a photo gate timer we're going to use where every time the beam is broken, it records the time. Okay, so we're going to be using one of those in our lab here in a little bit. So if you would, edit what you just wrote just a little bit. I told you that the length, the period depends on the length. Insert these words or these letters. Depends on the square root of the length. You can abbreviate SQRT for square root. Depends on the square root of the length. The period depends more specifically on the square root of the length. Kind of like when I doubled the mass, right? If I put 100 grams on here, it went pretty quickly. If I put 200 grams on here, it went more slowly, but it didn't take twice as long. In a very similar way to this mass having an effect, but not a doubled effect, similarly with the others. And then also, law number 2, it's going to depend, period depends inversely on the square root of gravity. Period depends inversely, little flecks of paint, depends inversely on the square root of gravity. Period depends inversely on the square root of gravity. Now remember our 4 laws of kinetic friction. 2 of the laws where this is what friction does depend on, 2 of them where you would think it depends on this but it don't. We're going to do the same kind of thing here with our 4 laws of the pendulum. The last 2 laws are, yeah, you would think it depends on this but it doesn't. One of those is amplitude, right? We would think the further back you pull it, the longer it's going to take, but no, law number 3, period does not depend on amplitude. Period does not depend on amplitude. Now, there's a little caveat. You remember with kinetic friction even, I gave a little caveat? Well, if you move it super slowly, then eventually, yeah, it's gonna... Okay, there is a point at which... there is a point at which if I pull it back super far, that it's going to lose a little bit. In fact, if I could pull it back, and I can't because this one's too long, but imagine if, I'm going to kind of angle it here, but if I pulled it back like this, so much of the weight is straight downward, it almost kind of throws things off. I was like, what is this going to crash into? So the period is going to rapidly change, right, as it kind of settles into a regular path. In fact, even pulling it back this far, because of the frictional forces, but also just the way the forces interrelate, it's going to kind of settle into a pattern where it kind of gets comfortable. And once it hits this comfort range, that's where it tends to be more consistent. It'll be a little inconsistent until it hits there. So technically, within 15 degrees on either side, which, I mean, that's almost nothing. If this is amplitude position, 15 degrees is that. But within 15 degrees, this is exactly true. Outside 15 degrees, it's mostly true. So if you want to put that little caveat, it doesn't depend on amplitude, particularly when you're within 15 degrees of equilibrium. You get outside that range, there's going to be a little bit of an effect because of the way the forces interrelate. But within 15 degrees, it does not have an effect. Fourth thing, it doesn't depend on the mass. It does not depend on the mass. Now, I do want to point this out. So law number 4, period of the pendulum does not depend on mass. Now, you may have noticed on the first pendulum we tested, there was a little bit of a difference when we went from 500 to 100. Ever so slight, but the real reason wasn't because of the mass. See the difference in the length? That was actually the reason. There's a difference in the length of about an inch in the atom total length. Of course, you're going to measure from the center of mass. Center of mass is about a half an inch off. So just a slight difference in length was caused by the difference in mass. And that was actually the reason for the tiny bit of variation, but it was so slight you really didn't notice. But if length is consistent, the mass does not affect the period of the pendulum. So when we put all those laws together, again, there is a cyclical nature, a periodic motion, where the motion repeats itself over and over and over in a cycle, if you will. And so our formula for the period is going to start out the same. T equals 2 pi, that speaks to the cyclical nature of L over G. Not M in case, because it's not mass and spring constant that affect things, but rather length and gravity. And if you wanted to, you could note that frequency still equals 1 over T. F still equals 1 over T. Frequency of oscillation. How many oscillations per second? Well, that's the reciprocal of the period. Look with me at just a couple of example problems now. Turn to page 154. Turn over to page 154. And look at example 10.6. Read that for us if you would, Kendall.
Find the period of a simple pendulum that is 0.75 meters long.
All right, so notice all they had to give us was the length, because that's really the main thing, right? As long as we're here on planet Earth, G is going to be roughly the same across the planet. Slight variations, but again, you're taking the square root of it, which makes the variations that much slighter. You're not going to notice a huge discrepancy. Length is the big thing that determines period of the pendulum. So they start with the equation, T equals 2 pi times square root of L over G. In for the L, they put the 0.75 meters. We assume 9.80 meters per second squared. Divide, take the square root, multiply by pi, multiply by 2, approximately 1.7 seconds. Really straightforward math. All right, look at 10.7. That one's a little bit more interesting, and read that for us, Audrey.
What is the length of a simple pendulum whose period is 1 second at a location where G equals 9.81 meters per second squared?
And we did this in the last problem with solving for the M, right? We could do the same for solving for the L. We would take the period, divide away the 2 pi, square all of that, and then multiply by G to get length. Well, they took the time, or the period we just said was a second. 1 second to swing all the way back and forth. Divide by 2, divide by pi, squared it, multiplied by, in this case they said G was 9.81 meters per second squared. Fine, multiply by that to get their length, and they said the length would be about 0.248 meters. Questions on how to use this. It's so similar to the spring, and it's almost easier because you're not usually going to have to calculate the G. Like the spring constant, sometimes we had to calculate it ourselves, right? Take the mg over x to find the k, then we could find period or frequency. The pendulum is going to be a lot easier math because the g is either going to be assumed or given. Questions on the pendulum. All right, for homework tonight, you're going to do 1 spring problem, 2 pendulum problems, 3 problems. It's page 157, problems 6 to 8. Page 157, problems 6 through 8 for homework this evening. We'll take a look at that in our next lesson. We'll also finish looking at some of those last concepts you read about with the physical pendulum. I think the mercury clock is really, really fascinating, mercury pendulum, and then a little bit about resonance as well. All right, have a wonderful rest of your day, and when the bell rings, you are dismissed.